Hello everyone. So today, as mentioned, I'll be talking about Git Your Secrets, overview of how Git works, some security issues related to this, then the prevention and resolution of those vulnerabilities, and then a quick dive into CI/CD systems, specifically GitHub, but the concepts transfer over to other ones such as Azure and Amazon as well. Okay, just about me, as mentioned, junior security analyst at Orange Cyber Defense. Previously, I did some development work as well as a little bit of embedded development. And currently, I'm volunteering as a staff member for Hack South, as well as an organizer for B-Sides. You can find me at Megalodon on Discord and IP Megalodon on Twitter. And then just giving an overview, these are the sections I'm going to go over. Firstly, just Git and GitHub, a very high-level overview, what they are, jumping into the Git server, dissecting Git on a very lower level, how it works, going back to the Git server, how that functions with Git, what can go wrong in these systems I've discussed, exploiting those problems, the prevention and resolution of these, and then, as I mentioned, a quick jump into CI/CD issues. That's a very deep rabbit hole that I'm only going to cover the surface on, and then the Q&A. First, looking at distributed version control, we have a difference between Git and your distributed platforms. Git is a version control system, if you were not aware, and then you have your distributed systems like GitLab, GitHub, Azure, can't remember the name, that stores these Git repositories, and this is to share your repositories and have a centralized point of storing that. You would want to do that for various reasons, but this is just an overview of how that would look or how that would function. You would have different PCs distributed or different networks or the same network, and that will synchronize to specific repositories, and those repositories might be a single one or distributed with a master server, depending on your layout and requirements. Now, it is important to note that Git is not a standalone tool, or Git server is not a standalone tool. Rather, it's a Git repository that's just configured with a specific server. That can be either a web server, an SSH agent, or a daemon. I'll cover those more later. And this basically allows for the remote sharing and retrieval, as I previously mentioned. Now, why you'd want to do this? Firstly, backing up. I mean, if your computer gets nuked, you might want to have that somewhere else, maybe a GitLab server at home to store your C2 repository. Hopefully, you have secure passwords on that. Then it allows you for collaboration with other developers, and also it allows for updates. Not many people see this, but a lot of the things you just use Git to distribute the updates of the software. It's a read-only repository, as they call it. And then this happens by using the modules of Git to facilitate the transfer of changes since your last synchronization. We'll cover this later on. Now, jumping into Git itself there, covering how Git specifically works. Git is at its core a content addressable file system. This basically means or the way it achieves this rather is by a key value store database. It is effectively just a system where you can pass the data. It gives you a SHA-1 hash of that data, and that's effectively the key for that data. You can then later on go pass it the key, and you get back the original data, as mentioned here. Now, the interesting part of Git is that you have access to the low-level tools that the Git version control system is built with. So, like demonstrated here, you can use the Git hash object and the gitcat file modules directly and use them to build other tools, for example. You don't necessarily have to use the high-level tools of Git. Then jumping into this a bit further, now that we have an overview of how the core of Git works, I mean, we have a database now, we can store stuff, but how do we translate that to actually having a version control system? So firstly, Git introduces another concept here called trees, and this is effectively just a file structure that allows you to have to point to specific or other objects. Now, example of that is in the right bottom. That shows just the different data types in a tree. On the left side, second left column, you'll see there's what's called blobs or trees. Now, that's effectively just your file system. A blob in this case is a binary file. A tree is another tree object. So you have trees that effectively represent directories here. And then from there, you can now point or emulate a file system effectively. From that, we now introduce a concept or another data structure for commits. This utilizes trees as well. It contains a tree. It can contain a previous commit or parent commit that it points to. And then it also has some other miscellaneous info, such as the author, messages, commit messages, and then other things like the commit email and such, but we'll not go into that into too much depth. And then your latest commit is referenced by the branch, and it's stored in the branch folder. I'll cover the specific structure of the .git folder on the next slide. But all of these things tied in and are all stored just in the .git folder. So basically, you have your latest commit now that's stored in or that's referenced by a branch, and that branch is stored in a folder in the refs folder. And then you have your current position of the repository, which is stored in the head file. And that is just in the outside here, right there in your .git folder. And it's literally just a text file, as we can see at the left bottom here, that has the text entry for refs head main, which just means it goes to the refs folder, the heads folder in that, and the main file in that, which just contains the hash of the object storing the... Sorry, let me just go one back. Yeah, there we go. There we have a larger version of it. So we have the objects folder there. Inside there, we have another folders there. You can see this called two characters. Now, what that refers to as I previously mentioned, when we put an object into the database, we get a hash back. Now, the first two characters of the hash, as on the right side bottom, so for example, 4935 and 44, those are created as folders. And within those folders, there's files created, which is the rest of that hash. And that's just a binary file containing the data of that file. And that's how Git basically references those files. There's also another file in this structure that's relevant other than the other one. So for example, you have your description there of your repository, you have your config file for the specific repository, you have the left side, the refs there. For example, your remote references, remote repositories are stored in there. You can have tags stored in there that I'll also cover a bit later. The heads refer to your different branches. Your hooks is local scripts or server-side scripts that can run. And then you have your logs file folder, as I mentioned, for the like the head and such. The two kinds, but there's also your packs folder. I'll cover how the pack file works. And then also you can contain inside the object info folder, there can be a object info packs file. And that's generated when you specifically run the Git in a server configuration. When the git update server info command is run for git dump servers, I'll cover what that means later. That basically covers or creates a list of all the pack files that exist. Because pack files are not referenced recursively, such as commits that references the previous commit. They all just exist there with a very long SHA-1 hash, or well, hash name, and it's very hard to know what the name is because there's no reference to them other than that specific file. I think that covers this slide. Just on the right bottom slide there to explain, the cat file -p flag basically just means it needs to print whatever we're passing to it. And that syntax for the main, it just basically points to the main, the tree of the main branch, just giving us an idea of what that currently looks like. Just getting to my actual screen again. Then, if we move over to the optimization of Git, I mean, surely Git can't store every single file. Like, if we have a massive file, let's say 2 gigabytes file, and we modify 1 or 2 bytes of that, surely Git can't store that entire file again? Well, it kind of does, until it doesn't. That's the thing. So normally, or originally, it'll store those 2 files completely separate because they have a completely separate SHA-1 hash. So they'll be stored in 2 separate folders or 2 separate places, just as is on disk. But then Git garbage collect gets triggered on quite a few different events, and that can be set by your config file. But in essence, what it does is it takes those massive files, it looks for similar files on your disk, and it stores them relatively to one another. So it'll create what's called a pack file, installed in that pack directly, as I previously showed, and it'll also have an index file that basically just tells Git, like, this pack file contains this, and this hashes. And the index file looks like shown here. On the right side, you'll see the size there. Now, here's an example of a file that's stored relative to one another. B042 is the one version of it, and 033B is the other version of it. But as you can see, the second one is very smaller and only references the top one, as you can see below that. Now, one interesting thing to note with this is that Git stores the most recent version as is on disk. So it's not like a backup system where you have the original file stored and any changes stored relative to that or incremental to that. It's done in reverse. So the most recent version is stored as is, and less recent versions are stored relative to that. Simple reason, you're most likely to use the more recent version, so you want it as is on the disk. Now, then going back to Git server, as we have a rough understanding of how Git itself works. Git server comes in 3 main flavors: your Git's with the SSH server, a web server, and Git daemon. You also have a smart and dumb variant of the Git server specifically. What that means is that with your dumb variant, it's basically just a bare repository, what we call. That's effectively just the .git folder, not any of the files on disk, because the .git folder contains all the files necessary to reconstruct the repository, as we know now, and with an Apache or Nginx web server slapped on top of that, with the pack file index, as I mentioned earlier, generated, so it can actually know what pack files exist on the system, if you don't have directory indexing enabled, for example. With the dumb variant, as I mentioned, you can just download the files directly, and the smart client is controlled by some of the Git modules. Those also come into play with the other methods, and the file transfer process remains fairly similar across the other 2 types of servers. As I mentioned, repositories are stored as bare repositories for basically all types of Git servers. Then going into a bit more depth, your dumb protocol basically has the following sequence of events. Your info refs file is pulled. That gets a list of, that contains a list of all the available branches. The head file is also read to see what the current branch is and what the current head commit is. The repository is then downloaded recursively, as mentioned, because you have the main commit and you know which parent commit it is from the data on it, and from that you can pull recursively all the commits until you get the entire history, and you have all the branch heads, so for each of them you can do the same process. And then if a commit can't be found, you want to pull that file, as I mentioned, you want to pull that objects info packs file, as that contains a list of what pack files exist, and then you can pull all the pack files from those directories, as you know what their names are from that file. That's important to note for later one of the attacks. Now, this differs a bit from your smart protocol, which is in use by both the smart HTTP server and the other 2 types of Git servers. So it's a lot quicker. You basically have the server that immediately, once a connection is established, sends the send back module, sends what the head points to, the available branches, and what functionality the server supports, such as its current version and things like that. Then the client just responds with what the hashes of the object that it requests. So example, if it's the first time you're pulling it, it'll get that from the head response that the server just sent it, and then the hashes of what commits it has, if it has any. And then the server just sends all the hashes that it knows the client needs from taking into account the difference. One interesting thing as well is this is done, the server response is done in chunking format at the end. So it just sends all the commit hashes or the commits that you need in a chunked format. And that's obviously far faster than just doing every one of them manually. Now then, moving over to what can go wrong with this implementation. We have to keep in mind that Git was originally implemented just as a local version control system and later to share repositories, but security was not taken into account when that was done. That was long ago, even before my time. So firstly, commit authors are not validated by default. I mean, why would you need to? So basically, I can put anything as my current email or username when I make a commit. I mean, that's not surprising. How is Git going to confirm that in the first place? Then you can access all the files in a repository by knowing the head or the main commit hash, as I mentioned. That's a feature, obviously. But the problematic side of this is also that if you have a .git folder exposed in the server, you're inadvertently creating a bare repository also there, which allows an attacker to pull down most of that repository, importantly. Then also secrets in a Git history tend to stay there. It's a version control system. It tends to do that. If you put in your secret there and you erase it later, it's still there. You just can't see it anymore, which is problematic in its own right. And then transfers using HTTP or the Git daemon, which uses an unencrypted protocol, can be intercepted and modified. I mean, I don't have to go into that into depth. It's fairly obvious if you're not encrypting it. But that's mostly been mitigated because most of your platforms, such as GitHub doesn't support that anymore. You're not allowed to use. It doesn't support the Git daemon, and you also can't send or use the HTTP protocol. And then also there's some deserialization issues such as insecure handling of symlinks and other binary issues that can happen. Though those are mostly in older versions of Git that has been patched. They're not that recently found anymore. There has been 2 minor ones, I think, in 2022 or such. And then there's a lot of other issues that come into play when we're looking at CI/CD pipelines, but we'll get to that. Then in terms of exploitation, our first issue, invalid or non-validated users, how can we exploit this realistically? So it's important to note that on a platform like GitHub, it still validates your type of access from the username and credentials you provided for your account, but it doesn't validate the authors of commits by default. So I can, for example, go here, enter my email as Linus Torvalds and my username as Linus Torvalds, and GitHub will happily display that Linus made that commit, even while that was most definitely not him. But as I mentioned, I won't be able to commit to his repositories because I don't have his level of access defined by GitHub. This becomes a problem in specific cases because I can, for example, make a pull request with some malicious code under the name of someone else, the repository owner or such, add some non-malicious stuff after that, and then if I make a pull request, that person might not look at the commits that has their name listed under it. I mean, they know they made a commit, so obviously it's not malicious. And then once they merge that, your malicious code is part of that repository. That can get very problematic when we're dealing with CI/CD pipelines, which we'll cover later. GitHub will, as I mentioned, GitHub will nicely display the profile image of the other account there because it doesn't do that checking by default. Then, for a second issue, expose.git folders. There's a few tools you can use for this. This also applies for SVN. That's before my time. I have no idea how that works. Once we have that repository downloaded, with a tool like Git Tools, the dumper tool, underneath that, there's a few other tools we can use to search that repository. Nice built-in tools to Git. They're useful for developers as well as attackers. And then, there's a lot of other searching tools that you can use to search repositories as well as GitHub. yeah, just to run quickly through them, you can search specific files using the git cat file, specifying the hash of the file and just doing normal grep. You can use the git unpack objects that unpacks all the object files into files on the disk. This makes it possible for both that command and the other commands to work. Otherwise, you can't read those files because they're not actually on disk. Git's just not going to see them because it's such a low-level command in Git. You can also search through the entire history of Git. That command basically, your git rev list -- all basically just gives a list of all the commit hashes. The file hashes, sorry. And then the git grep searches those file hashes, retrieves the file, and searches the rejects through those files. So that's a very quick command that allows a very powerful search across an entire repository history, all the files in that repository with rejects. I mean, what more could you want? Then you can also search your git log with -s. That's colloquially referred to as the git pickaxe option. This takes a string as an option and shows only the commits that changed where the number of occurrences of a certain string changed. So for example, this is useful when you want to search for a certain function name, whether the function name was introduced or such. You just add it there and Git will spit out the commits where the number of those occurrences changed. Just going into a bit more depth, if you have an example of a repository like this served by a Python web server, we can use our nice git dumper script, just locally in this case, and that pulls an entire repository. Now, as you can see there, we have a nice red one there. That file might sound familiar, the objects info packs. Reason for that being that file was not generated because this is not supposed to be a Git server. We're not supposed to be pulling these files. Hence, that specific file was not pulled, was not generated, and hence we have no idea what pack files exist on this server unless they also left directory indexing enabled, which is a problem in its own right. So we'll only be able to pull the files that are not stored in the pack files, but that's still a significant part of the repository. Then further, let's say we've pulled if we've now pulled that repository, we have an example file here called sever.py, just listing the first 13 lines. We can see they're making great use of environment variables. No environment variables in the repository. It's a bit of we can't see much of that. That's how it should be done. Problematic is if we search the repository with that command I previously showed, we can see there's a previous version of that file that does have the key. And what's the chances of them not having changed that key? Probably high. Don't do this. So even if the advantage is if this happens, you can just change the key, but try to not do this in the first place. There's also other metadata that can be used when you have a repository pulled like this, such as as I mentioned, you have the config files. So you can see remote repositories that's linked to this, upstream repositories. Those might include internal hosts or other data like that. And you can also include or also find information about the committer in the config file, which might be useful. Then if we move over to the prevention and resolution of these three rough issues. Firstly, for the unvalidated authors, we have this nice thing called GPG keys, which got implemented. You just add your GPG. You could generate a GPG private and public key. You add your public key to GitHub, so it can confirm that or confirm to other people that you are indeed the person that made those commits and tags. And then in Git console, you can make specific commits and tags signed by that GPG key. Tags are simply, the specific type of tag, your full tags, or basically take a repository in a specific point in time and validate the SHA-1 hash effectively of that entire repository. And you sign that with your GPG key, basically proving this repository, this point in time, is valid and signed by me. And it can't be modified without changing the signature of that. Then you can sign specific or individual commits with a -s, capital S flag. And you can also configure this to be true on all commits, which is probably what you want to do with just setting your Git local configuration or global configuration with the commit.gpg sign true. and then you can use the -v flag to just verify that the signature. On the GitHub side, it looks like this. As you can see, there's the verified badge on the right side there. If you make a commit from GitHub itself, you might have seen this, it'll also automatically add that because it knows you have access to the account, hence it's a verified commit. I do recommend setting this up. Then moving over to exposed Git folder. The most important thing with this is being aware of this. When you're deploying a repository, it's very easy. You go into your web boot, git clone, get your server on there, make your changes, commit it. But don't forget that .git folder. You might not see it with Alice, but it's still there. So ideally, you'd want to have your server rules, have a global deny rule, maybe for all files and folders starting with dot. That's generally stuff you want hidden and not served on a web server, other than dot well known. Hence, this rule showing how to exclude that. One important thing to note here, as I have seen it before, don't just block access to like .git folder. Block access to the content within it as well. And then, yeah, you can also set applicable permissions on your .git folder and other folders, so that can't be read by a web server client, web server user. You can use some automated scanners to pick this up, though that's obviously more of a resolution than a prevention. You want to avoid that, but that's a good second layered security step to have in place. And then also recommend doing manual testing, going to your servers now and then, checking that your .git folders are not exposed, because it's not always going to get picked up. Then if we look at the prevention resolution of secrets in your Git histories, this is far easier to prevent, like many of your other security issues, than to resolve or to detect, for that matter. Pre-hooks are scripts that you configure with your .git folders, .git repositories on client and server side. They can basically be any type of script. You can set it to scan or check for certain credentials, though that's still a manual process. You're not always going to pick that up, but it is another layered security to have in place. There's other tools like Git Guardian that you can implement. Those scan your entire repository, the history of it as well, for commonly known credentials and things that look like credentials or passwords. They give you quite a few false positives, but it's far better than missing stuff. But the most important thing is to keep this in mind. Git remembers. It's very hard to remove something from Git, and it's far easier to just not have it there in the first place. There's the option of revoking those credentials once you have put them into Git, and you can rewrite your Git history. That becomes a bit complicated, especially when you're dealing with a distributed repository where other people are working on that as well. There's other things such as just implementing a .git ignore file for .env files and such that you don't commit or your environmental files to your repositories. Do that from the start, and then also rotate your secrets for each deployment environment, so that even if you commit secrets to your repository, that is only for your base repository, and that's not used on your UAT, dev, or production environments. Because if it's not used there and you compromise the repository, that doesn't help you much, because the secrets are changed. Then just in general, keep Git updated. As I mentioned, there's been issues in the past with Git, like many other pieces of software. For Git servers, your regular vulnerabilities and misconfigurations still apply. It's still a web server. It's still a SSH server. Your normal misconfigurations are still going to be issues there. It's not different because it's a Git server. So whenever possible, use an existing platform like GitLab that's specialized for that, if you need to host it locally, or GitHub, your Azure repos, or any other platform that already does that for you and is specialized for repositories. And then finally, small thing, when you delete a repository, also delete that hidden .git folder. Otherwise, you can restore that entire repository with everything inside it. If we then move over to CI/CD, what is CI/CD? I don't want to sound like a marketing person here, so I'm going to quickly cover it. CI/CD, continuous integration, continuous deployment. That's basically like automation for developers that want to automate the integration, and they want to automate the deployment to servers because it's a pain to do that every time manually if you're making 200 changes per day. And then where does this take place? So mainly this is broken up into two places. You can have your runners on GitHub or the other platforms. You have like GitHub Actions that automatically triggered with YAML files. And you can also have your Arc or your self-hosted runners, which is basically a tool you install or a daemon you install on your server. And that authenticates with your server. And then your platform basically schedules any build or compilation and deployment tasks to those servers that you have. That comes with its own perils and issues, but we'll cover that a bit later. As I mentioned earlier, or in the first complete start, I'll mostly be covering GitHub Actions, but this draws over to your other platforms as well. Further on, if we look at CI/CD specifically, the NSA has a nice guideline for that. They cover three main threat points. It's firstly your compromise of your credentials in terms of a developer, in any type of access from their side that gets compromised. Secondly would be a third party that gets popped. Maybe a NPM repository that you're using gets popped. Remember, if you're building your application and that pulls in a compromised NPM repository in that build pipeline, that compromises your build pipeline and everything associated with, or rather poisons it, yeah. And then you can also have supply chain compromises once you've, in certain specific parts of your CI/CD pipeline, that can modify parts of that pipeline, like your building parts, and that can be very hard to detect as well, once that's already there. One good example of that is Sunspot. That was your SolarWinds attack, the specific one that modified, or it modified the build part of the binary, that was involved with the supply chain track for that. And because it's in there, I mean, you have a binary there, and before that binary, it's source code. So it's kind of odd. You don't have a SHA-1 hash or something where you can compare the two and see a difference or a change that shouldn't be there. A good resource to look at also for CI/CD in general that I would recommend is the GitHub Actions Code repository that covers a few of these in more depth and gives an example repository to actually play around with that and see how it works. This is an overview of the NSA guidelines as well. As you can see, there's a few attack vectors. This is specifically for AWS, but once again, these draw over. Some of these are specialized, but it's good to keep them in mind in general. There's also OWASP CI/CD top 10 risks. I did not know this before this presentation. I do recommend looking at that. I haven't had time to work through them, and I don't have time to cover them all in these slides. Definitely not. So I'm just listing them there and recommending you take a look at those. Now, if you look at the GitHub documentations for their CI/CD pipelines, that warning there basically tells you in short words, if your pipeline gets compromised, you have problems. It's not good. And to prevent those problems is not easy, like once it's compromised. Like, for example, exfiltrating data. They literally describe two methods here to exfiltrate data from the pipelines that they admit they can't really stop you from doing that. Because it inherently would break a lot of functionality of how these runners or pipelines work. The first will be where you just pipe it out to obfuscate it to your terminal, the log lines, and the second being to send it out to a remote server. You maybe have a jump box running a Python web server, and then you can exfiltrate your GitHub token on that. One potential fix for this, that does require quite a bit of configuration, is the step security, what do you call this? The I'll get to the name later. This is basically a firewall and file monitoring service within your pipeline. So you basically add this action to a repository. This is just an example on the GitHub Actions Go repository specifically. And it can monitor for specific things. It acts as a firewall both on layer 3 and 4 as well as your DNS. So you can specifically specify URLs and such that are allowed. Now this works great for a pipeline like this because you're supposed to have quite a great baseline on that. There's not supposed to be quite a bit of variation on that. So you should be able to have specific URLs and IP addresses specified in there that should be allowed and everything else blocked. The other thing it does is once those other IPs that shouldn't be triggered gets triggered, you get alerted, and it can block it, of course, as well. It also it's also able to monitor the changing of certain files. So you can tell it certain files are not allowed to change through this build process or be modified in any way. And if that does happen, you get alerted, the run gets blocked. Now, as I mentioned, a configuration like that takes time. It needs to be maintained, but it does block that one avenue of attack where your pipeline to get compromised. So it is still definitely recommended to look at that. Another type of attack that's a bit out of those initial 3 vectors that I described, and it's a bit more specific for your platform, is something like this. So GitHub, as I mentioned, you have your GitHub Actions, that one from YAML files. So this is one example YAML file that basically just checks if the pull request title starts with Octocat. Now, this is just an example. Can anyone see the issue here? Now, if we consider that on the right side is a valid name for a branch, and we create a pull request for someone's public repository that does this, I see issues. And those issues look like that at the right bottom. If you have something like this, that gets pulled in, that repository title gets pulled in, and you basically have code execution or code injection within your pipeline. So your attacker basically takes over your pipeline without you doing or without any action from your side, because this is an automatic action that gets triggered when a pull request gets opened. There's quite a few ways to fix this, but the important part is to take into account there's other vectors of attack like this that isn't limited to, or that gets involved into a platform like GitHub that you need to take into account. So it's not just the initial 3 vectors, it's also things like your build actions. You need to take into account when those run, what type of user input gets input on those, and what type of access other people will have in that types of environment. GitHub or GitHub Actions does quite a good job in terms of locking this down. They prevent you, like the GitHub token within a runtime is only limited to that runtime, for example. There's quite a few other things. I do recommend checking out the documentation for your runtime, whether it's GitHub Actions or whatever one you're using. There's specific recommendations that they tell you to keep in mind, and it's going to be specific for each one you run. Now, for the one I mentioned, there's 2 recommendations from GitHub side for something like that. It's firstly just to have a user action instead of the inline script, because then it's not evaluated at specific point in time. You assign it to a variable, that variable gets passed to your action, or using an immediate environment variable that it gets evaluated at that point and then passed to the action that gets executed after it's been evaluated. There's a few of my references, and then yeah, thank you.